Okay, so this is part two of the animation of the Brave hair, and we did the rigid body system first. Now we're going to move on to the spring mass system, where they kind of tweak the system so that the hair looks a little more realistic. So we'll move on to that and show you the exercise for that right after this video and the questions after.
In the last exercise, you probably noticed that the simulation lacked the natural bounciness of hair. But what makes something look bouncy anyway? To make this model bouncy, we need each strand of hair to expand and contract slightly when forces are applied to them. This required a new physical analogy to base our model on, so we tried springs. Springs are great because they can change length when you pull on them. And to give the hair a little bit of weight, we add a small weight to the end of the spring. This is known as a mass spring system. We can actually draw a mathematical model to explain what happens when a spring expands and contracts. The model we use is based on a law developed by Robert Hooke, a 17th century physicist. Hooke noticed that there are two things to consider when a spring expands and contracts. 1. If we pull on a spring and it expands, we will increase its length and it will pull back together. 2. If the spring contracts, its length will decrease and it will push apart. How much a spring pushes and pulls is known as the spring force. Robert Hooke was looking for a relationship between the spring force and the amount the spring contracts or expands. We call this change in length displacement. Displacement is defined as the current length minus the rest length of the spring. When we stretch a spring, the displacement is positive and the resulting spring force is negative. This is known as the pull force. When we compress a spring, the displacement is negative and the resulting spring force is positive. This is called the push force. So Hooke's observation was quite simple. He noticed that a larger displacement results in a larger force, while a smaller displacement results in a smaller force. That is, he noticed that the displacement is proportional to the force. However, every spring is different. Some take a lot of force to displace, and some are really easy to displace. So Robert Hooke introduced the idea of stiffness to account for how hard it is to displace a given spring. It is represented with the letter K. This led Hooke to his final equation, which is known as Hooke's law. The spring force is proportional to its stiffness times the displacement. Notice that there is a negative sign there. That's because we want a positive force when the displacement is negative and a negative force when it's positive. If we plug this equation into the computer, we get this realistic spring behavior. For Brave, we modeled the horse's hair using a mass spring system similar to what we are describing in this tutorial. Nearly 10,000 simulated hairs in total. In the next exercise, you can explore a simple mass spring system. You'll be able to adjust the following parameters: mass of the particle, spring stiffness, K, and the force of gravity, and we'll ask you some challenge questions to make sure you understand the basics of Hooke's law.
Okay, so moving on here, they have some questions for us to answer. But also experimenting with like the spring. This isn't, on this exercise, we're not going to save anything on here, but it's just a way for you to see how it works. So we're kind of showing you the demonstration of how spring stiffness will affect the movement. So obviously if it's less stiff, then it's going to have more movement. More stiff, it will have resistance to the movement. So if you pull on a spring to stretch it, the spring will generate a force in which direction? So the same direction as the force, the opposite direction, or a perpendicular force. So do we need a hint? Should I check? Oh, that's not right. So it's really, I think it's the opposite, yes. So going through those questions, you'll go through all 7 after having watched all those videos, and you can kind of see the effects when you're using this exercise. So I won't go through all 7 with you, but what we will do is go through this video and then get to the exercise that we need to do in Google Classroom.
Now that you are comfortable with how springs expand and contract, we can try something a little bit different. Let's try connecting a bunch of springs together, like this. When we simulate springs, we don't draw them using the zigzag pattern. Instead, we use lines which can expand and contract. This gives us a really bouncy strand of hair. But it's a bit too bouncy. Notice the hairs take a really long time to settle down. This isn't very realistic. Take a look at our reference shots again. See how quickly the hairs come to rest. Just a few bounces. You might think changing the spring stiffness will fix this, but look what happens. Both low and high stiffness values still result in hair which never settles down. Our solution to this is adding what's called a damper to each spring. A damper is something that resists fast changes in displacement, and it's used to bring springs to rest much more quickly. Check this out. Here we have the same strand of hair as before, except each spring is connected to a damper. And we can change the amount of damping using this new parameter. If we increase damping, the springs resist quick changes and therefore come to rest much faster. However, too much damping will result in really stiff hair, which isn't natural. And here is what it looks like with a whole bunch of hair. We went through a similar exercise in the early stages of modeling Merida's hair. We were trying to get the right mixture of spring stiffnesses and damping so that we could achieve the desired artistic look. But with the wrong settings, the springs start fighting each other, and you get pretty funny results. So the trick is to find a nice balance between spring stiffness and damping. You can try this out in the next exercise. Here you can control damping of each spring, number of hairs, number of springs per hair, and spring stiffness. See if you can come up with something that behaves a bit more realistically.
Okay, so now on to spring mass system exercise. So you'll be again working with the hair simulation. You use your mouse to left click and drag to see the effects. And you're going to do your before picture for the Google Classroom assignment so we can see the original dial settings, so 5%, 20, 5, 20, and 4. That way I know you started at the beginning. And then you make your changes. And again, there's no real right answer here. We're just trying to make the hairs look as realistic as possible. So this is really just a matter of you playing with it, to be honest. So springs per hair, you've got number of hairs, you've got damping. So you can see 2% is way different than 20%. Well, let's do this again. So 0% damping looks like that. And you can see the effect with less hairs. And then if I go up to 20%, it's like you're in syrup. So these are different things that you can change to get some realistic looking, bouncing, curly red hair by changing spring length, springs per hair, spring stiffness. So again, no right answer, but I just want you to experiment and see what the effects are. Because again, this is a model in simulation that the Pixar Studio artists actually used to make these videos. So now you get to use them. So do your after picture once you've made your settings and turn that into Google Classroom, and we will move on to the third and final exercise, which has to do with support springs.